Microsoft's General Artificial Intelligence team has dropped a new AI called BitNet B1.582B4T. And yeah, the name sounds like a Wi-Fi password, but the idea is surprisingly elegant. Run a serious large language model on nothing more exotic than a vanilla CPU without wrecking your electric bill. The kicker, they're doing it with weights that aren't 32-bit or 16-bit or even the crunchy 8-bit you've heard about. Instead, every single weight in the network can only be -1, 0, or +1, which averages out to just 1.58 bits of information. In other words, they've squeezed the precision so hard that 3 possible values cover the whole show because the log base 2 of 3 is 1.58496. You get the picture. Now you might ask, hang on, don't we already have 1-bit or 4-bit quantized models? We do kind of, but most of them were full precision models first and got compressed after the fact. That post-training quantization trick saves memory, sure, yet it generally leaks accuracy like a balloon with a slow pinprick. Microsoft flipped the script by training bit first. They let the model learn from scratch in Ternary, so there's no memory of the float point life to miss. The result is a 2 billion parameter transformer trained on 4 trillion tokens. And the team insists it keeps up with heavyweight open source rivals that still carry all their float baggage. Let's talk hardware impact because that's where this gets spicy. A regular 2 billion parameter model in full precision parks itself in something like 2 to 5 gigabytes of VRAM. Once you ditch the embedding table, BitNet strolls in at 0.4. That slashes the working set so hard that the model fits comfortably in the L cache layers on many CPUs, which is why the demo on an Apple M2 chip spits out 5 to 7 tokens per second. A regular 2 billion parameter model in full precision parks itself in something like 2 to 5 gigabytes of VRAM. Once you ditch the embedding table, BitNet strolls in at 0.4. That slashes the working set so hard that the model fits comfortably in the L cache layers on many CPUs, which is why the demo on an Apple M2 chip spits out 5 to 7 tokens per second. About the speed at which a human reads a paperback line by line. And while it's generating, the researchers measured 85 to 96% lower energy draw than similar float models, which is basically the difference between idling a Prius and flooring a muscle car. Yet, of course, none of that matters if the answers stink. So the team hit it with the usual alphabet soup of benchmarks. MMLU, GSM 8K, ARC Challenge, HellWagPi QA, Truthful QA, the greatest hits averaged across 17 different tests. BitNet lands a 54.19% macro score, barely a point behind the best float-based competitor in its weight class, Llama-derived QN 2.5, which sits at 55.23. Where BitNet really flexes is logical reasoning. It tops the chart on ARC Challenge with 49.91%, leads ARC Easy at 74.79%, and edges past everyone on the notoriously tricky Winnow Grand with 71.9%. Math isn't a fluke either. On GSM 8K, it cracks 58.38 exact match, outscoring every other 2 billion regular model on the list and beating Quen's 56.79 while running on maybe a tenth of the watts. If you're wondering how that stacks up against 4-bit post-training tricks, the paper spells it out. They took Qwen 251.5B, threw the standard GPTQ and AWQ int4 hammers at it, and got the memory down to 0.7 GB. Nice, but still nearly double BitNet's footprint. If you're wondering how that stacks up against 4-bit post-training tricks, the paper spells it out. They took Qwen 251.5B, threw the standard GPTQ and AWQ int4 hammers at it, and got the memory down to 0.7 GB. Nice, but still nearly double BitNet's footprint. More importantly, the quantized Qwen dropped 3 full points of accuracy to the low 52s while BitNet held its 55-ish line. So the morale is native ternary greater than retrofitted in 4, at least in this neighborhood. Now let's peek inside the model. I'll use simple examples, so even if you're not super technical, you'll get the idea. Think of a normal AI model as a huge warehouse full of shelves. Every shelf is packed with big jars of exact numbers, and anytime the model answers a question, it has to haul all those jars around. BitNet replaces the jars with tiny color-coded poker chips, red for -1, white for 0, blue for +1. Because there are only 3 kinds of chips, they weigh almost nothing. So the whole warehouse shrinks from a few gigabytes down to about the size of a single mobile game download. A little worker called the ABS Mean Quantizer decides which chip fits each spot and does it live while the model runs. Meanwhile, the messages racing between shelves get squeezed into kid-sized Lego bricks, 8-bit numbers, so the corridors stay clear and everything moves faster. That chip and brick diet can make the structure wobble. So, the designers add a sprinkle of balance powder, that sublayer norm, and they swap a fancy activation function for a simpler squared ReLU because simple handles rough treatment better. That chip and brick diet can make the structure wobble. So the designers add a sprinkle of balance powder, that sublayer norm, and they swap a fancy activation function for a simpler squared ReLU because simple handles rough treatment better. They also borrow Llama 3's Tokenizer, which is like bringing an already filled dictionary so the model doesn't have to learn a new alphabet from scratch. Why train it in 3 rounds? Imagine teaching a child. First, you read them every book in the library at top speed. That's the 4 trillion token pre-training with a high learning rate. Halfway through, you slow down so the kid stops skimming and starts absorbing details. That's the cool down. Next, you give them practice exams with clear answers, the fine-tuning stage. So they learn how to talk to people without rambling. Here the teachers discovered that adding up the grading points instead of averaging them keeps this low-bit brain steadier. And because the tiny poker chips don't explode when you poke them, they could push the lessons a little harder. Finally, you show them pairs of answers and say, "People like this one better. Do more of that." That's direct preference optimization. So, the student keeps their knowledge but learns some manners. Crucially, the kid never switches back to heavyweight textbooks. It's chips and Lego bricks all the way through, so nothing gets lost in translation. Running the model needs special plumbing because graphics cards expect normalized jars, not chips. Running the model needs special plumbing because graphics cards expect normalized jars, not chips. Microsoft wrote custom software that bundles 4 chips into a single byte, slides that bundle across the GPU highway, unpack it right next to the math engine and multiply it with those little 8-bit bricks. That trick means BitNet can read 5 to 7 words a second using nothing but a laptop CPU. If you don't have a GPU, the BitNet CPP program does the same dance on a regular desktop or Mac. You only need about 400 megabytes of spare memory, so even an ultrabook can play. The payoff shows up on a simple graph. One axis is memory, the other is test score smarts. Most small open models squat in a blob that needs 2 to 5 gigabytes and scores somewhere in the 50s. BitNet lands way over to the left at 4 gigabytes, yet floats above 60 on the scoreline. Even bigger rivals that were later crushed down to low bits can't catch it because they still lug more memory and fall a handful of points behind. In plain terms, BitNet squeezes more brain power into every byte and every watt, which is why it looks like such a leap forward for anyone who wants solid AI on everyday gear. Naturally, Microsoft isn't calling it job done. The final section of the paper reads like a to-do list. They want to test how well native 1-bit scaling laws hold at 7 and 13 billion parameters and beyond. And they're practically begging hardware designers to build accelerators with specialized low-bit logic so the math no longer has to pretend ternary values are int8 refugees for decades. They also admit that the current 4K token context needs stretching for document length tasks, that the data was English heavy and should branch into multilingual territory, and that multimodal text plus headbug hybrids are still uncharted for the Ternary approach. The final section of the paper reads like a to-do list. They want to test how well native 1-bit scaling laws hold at 7 and 13 billion parameters and beyond. And they're practically begging hardware designers to build accelerators with specialized low-bit logic so the math no longer has to pretend ternary values are int8 refugees for decades. They also admit that the current 4,000 token context needs stretching for document length tasks, that the data was English heavy and should branch into multilingual territory, and that multimodal text plus headbug hybrids are still uncharted for the Ternary approach. So, expect papers on lost landscapes and bitflip resilience in the months to come. But let's zoom out. What BitNet B1.582 really shows is that we might not need a farm of H100s to push useful AI into everyday devices. If you can carry a model that rivals the best 2 billion millimeter floats in 1/5 of a gig and push it at reading speed on a single CPU core while sipping 30 milligaules a token, then smart keyboards, offline chatbots, and edge device copilots suddenly look plausible without tripping over battery life or data center bill. You can grab the packed weights right now on Hugging Face. 3 formats, in fact. The Inference Ready Pack, the BF16 Master for anyone crazy enough to retrain, and a GGUF file for BitNet CPP. And there's even a web demo if you just want to make it tell dad jokes before bedtime. Oh yeah, everybody loves the giant models with 100,000 token context windows and billion-dollar clusters, but BitNet B1.582 is a reminder that sometimes a tight coupe beats a roaring muscle car. If the streets are narrow and gas costs a fortune, keep an eye on this space. Once the hardware catches up and the sequence length grows, we might see an all-out Ternary renaissance. Until then, grab a CPU, download 400 megs of weights, and see what a 158-bit future feels like. Thanks for hanging out. Smash the like button if you learned something, and I'll catch you in the next one.